Hello, everyone. Can you hear me? If someone can type something. Okay. So glad to see you all back here. This is lecture number or webinar number 7 in the Stark at Home series. And as you can see from the background, it's a little bit of a cheat because this is not Stark at Home. This is more Stark at Office. Gladly, at least here locally, things are starting to go out of lockdown mode. So roughly half of the days of the week, folks at Starkware can go back to working. So you can see, my office here. Anyways, today we want to talk about the Cambrian explosion of ZKPs or crypto proofs. And to that effect, I'm going to increase a screen here. And we'll go over a deck of slides that I actually used when I gave, together with Alessandro Chiesa, chief scientist at Starkware, and my co-founder and collaborator for many, many years, roughly 10 or so, on all things snarks and starks. And of course, a very important independent researcher in this field. Anyways, both of us gave talks there at the time, and this is based on the slide deck there, but I'll maybe also try to use the scribble pad from time to time, explain stuff. So without further ado, I want to talk about the I want to make this thing larger. Okay, cool. So I want to talk to you about Cambrian explosion of crypto proofs. So the Cambrian explosion refers to this period roughly 500 million years ago, where from some primordial soup that had almost, no variety of creatures, things sort of suddenly emerged, and then we got this many different kinds of animals and so on and so forth. And it seems, looking back over the past sort of 10 years or so, and certainly the pace is picking up. We're seeing more and more variants of zero-knowledge proof systems. And what I want to do is to sort of go over, from a very, very high level view, go over the common denominators, but also the kind of distinguishing factors between them, okay? I'll stop from time to time and just ask if you have questions. So just checking back, can you hear me? Is everything okay? Can you see the screen? Can someone type? Okay, and then for those who are new here, I'll just say that from time to time, okay, I'll go back to most of the time I'll be staring at the screen that I can't see any feedback, but from time to time I'll go back and there's the Ask a Question tab that you are invited to use, and then I'll ask some questions and go back and forth. Okay, good. So when I first used this slide, it was in September 2019, and already we used so this was part of Starkware sessions, and we already talked about the Cambrian explosion of ZKPs, and we posted a whole bunch of proof systems that appeared there then, and we said, look how many of them there are. And then a few months later, we already had to populate it with significantly more. And because this is sort of more laid back in the Stark at Home, so I haven't done a literature survey to sort of populate it with more and more. And also there's a limit to the size of to the amount of information that can go on this screen. But there is a lot of proof systems out there. And one thing that I sort of let's clarify up front is which ones of them are Starks, which ones of them are Snarks, what's the relation between the different kinds, and what do we say when we mean a Stark or a Snark is one the other, or the vice versa? Because I think there's some confusion out there, and I want to first of all just address this thing. I also want to say that since this is going to be roughly a 40 or 50-minute talk, and if you just count the number of pages of dense math that are covered by the papers that are up here, and of course they're based on other papers, it's easily more than 1,000 pages of dense, math and computer science. So there's no way I'll do anything close to, I'm doing a big disservice to the amount of innovation and complexity that goes into all of these different contributions. But that's a necessary thing when you talk about high-level stuff. Okay, so I want to just start and tell you a little bit about what are Starks and Snarks. And so they all come from this larger family that I like to refer to informally as proofs of computational integrity, or in other cases, things like cryptographic proofs or crypto proofs. And the reason I like to use one of these two phrases is because actually you won't find a formal definition of crypto proofs, and you won't find a formal definition of proofs of computational integrity. And in that context, it's actually a feature, because once you give a strict mathematical definition to some term, then you start having problems, because there might be things that look very much like it but are not exactly that thing, and then you sort of have this problem. At least as a mathematician, you want to be very concise, but you also want to give a flavor. So when I talk about crypto proofs, as was in the title of this talk, or proofs of computational integrity, it's this big area with many different flavors and constructions that satisfy different constructions, and we just want some terms that without giving a very formal definition. So here's on the left, you see some sort of wish list of what kind of magical properties would you like from your proof systems to have. So you would like them to be privacy preserving, to shield the inputs that you care about. And this is the property that is known as zero knowledge. And I want to say already, so often people talk about ZKPs as this whole big domain, but zero knowledge is a very concise mathematical definition that has, and many of the proof systems that are deployed out there and go sometimes under this informal name of ZKPs are actually not ZKPs formally, which is again why I like using the more sort of vague and loose term. So one property you would like from these proof systems is the ability to shield some of the transactions. Another one is the property of scalability, which means that you would like the time needed to generate a proof to be as small as possible, and the time needed to verify a proof be as small as possible. And it's with respect to the size of the computation. So for instance, if your computational statement discusses, the correct settlement of 10,000 transactions, or a million transactions, and T is this parameter, it's maybe the block size or the gas amount or the number of computations, you would like that as this parameter T scales up to infinity, you would like the prover running time to be as close as possible to T. It cannot be smaller than T for, there are provable mathematical reasons why it cannot be smaller than T, the proving time. And you would like your verification time to grow as slowly as possible. And again, there are mathematical reasons why verification time cannot be less than logarithm of T. So the best you could hope for is to have the proving time be actually, very close to T, and the verification time being close to log T. And any proof system that has both of these things at the same time, both nearly linear or close to linear proving time and logarithmic or polylogarithmic verification time, is something that we will mathematically call a scalable proof system. So scalability is another aspect that you would like. And the exponential separation between the proving and verification time is extremely helpful for scaling up, proof systems, blockchains and computations, and allowing blockchains to scale up. Another aspect that you would like is universality. You would like your proof systems to cover as large a range of computational statements and problems and apply to general computation. You would like them to also be transparent, which means that when you set them up, and when you look at what the verifier needs in order to trust the correctness of the proving system, the only thing you need to trust is that the queries or the setup had enough randomness in it or enough entropy. And this randomness or entropy should actually be transparent, meaning done in the public domain using public random coins. And you would also like, to the extent possible, to have lean and battle-hardened cryptography. Now, any system that has the two properties of any proof system that has the two properties, one of them is scalability and the other one is transparency. And there's the ARK part. I don't want to talk about it in this talk, right? It also has some mathematical definition, which means the ability to extract a witness whenever you see a correct proof, but let's put that on the side. So proof systems that are scalable and transparent are Starks, and that's the S and the T. So the S in Stark is scalable, and the T in Stark is transparent. And as you see here, so not all proof systems, or even not all proof systems that have desirable properties are necessarily Starks, and Starks don't necessarily need to be universal or to have lean and battle-hardened cryptography. If you also have the zero-knowledge aspect, you would call it a ZK Stark. And I want to now show you or discuss a little bit the differences between the mathematical definition covered by a system that is a Stark and the mathematical definition that is covered by a system that is a Snark. And then we can look and see which systems are Starks, which are Snarks, and which are neither or both. And it's really this sort of Venn diagram thing, right? Some of them are Starks only, but not Snarks. Some of them are Snarks, but not Starks, and some of them are both. Some of them are neither. Okay, so a Stark must be transparent, meaning no toxic waste, no trusted setup, period. They must be scalable, logarithmic verifying time, and quasi-linear proving time, close to linear proving time. Both of them must hold, and they must require a succinct setup. So whenever there is a setup, it must take at most logarithmic time in the amount of the computation. So a system that satisfies these three, or the emphasis is on these three properties, then we call it the Stark. Snarks, again, this is a mathematical definition that puts its emphasis on other things. So first of all, a Snark, the N there means it must be non-interactive, which means that the proof must be a single message after pre-processing. It turns out that you cannot have a proof system that is fully non-interactive, period, like with no pre-processing or no setup phase. It's mathematically impossible, or it's impossible for interesting languages and interesting computational statements. But the best you could hope for is to have some pre-processing stage, and after that, everything should be just a single proof being sent. And a Snark must satisfy this. It must be succinct, which is basically half of the definition of scalability. So the verification time must be logarithmic. The proving time could be more than linear, it could be quadratic or more, it would still be qualify as a Snark. And the setup can take linear time or more. That's okay under the definition of a Snark. A Stark cannot allow this. So in particular, you can see that non-interactive Starks are Snarks and are actually transparent Snarks. And you'll see in the literature, sometimes people talk about transparent Snarks. And also transparent Snarks can always, under the Fiat-Shamir heuristic, as long as they have a succinct setup, sorry, I wanted to say the other way around. So if you have a transparent Snark, that's the bottom line on the left side. So if you have a transparent Snark with a succinct setup, that would be a Stark. And if you have a Stark and you run it in non-interactive mode, say using the Fiat-Shamir heuristic, and sort of then it is converted into a Snark and a transparent one. And some of papers in the literature refer to Starks as transparent Snarks. So now going back to this picture, as you can see, some of the systems out there that we'll soon discuss and sort of understand what goes into them and how they differ. Some of them are Starks, some of them are Snarks. I want to point out that any one of the systems there that have a T around it, if you apply the Fiat-Shamir heuristic to it, then you actually would get a Snark. You could also, a transparent Snark, you could also get a, you could also run them in an interactive mode, say taking your randomness from the blockchain, and it would still be a Stark, but in that case, it would definitely not be a Snark. Okay, so this is sort of just clarifying what, from a mathematical point of view, satisfies one thing or the other. So now I'll pause and ask if there are questions. And I see there is a question. Let me just, okay. Okay, the question by Aline. Snarks have constant verification time by relying on non-falsifiable assumptions. No? Or maybe on miscounting the witness input verification key size. Can you clarify what you mean by saying you cannot have less than logarithmic verification time? Yeah, so let me clarify, because it's actually, so Aline, thanks for this question. It's a very good one, because there's a lot of confusion around Snarks having O of 1 verification time. So Let me, with your permission, basically, I will use the writing pad that I prepared here. So I will now basically share a different screen just to answer this question. So let me see now. I need to go, bear with me just 1 minute. I need to stop sharing this screen and then share a different screen, which will allow me to, good, this should work now. Great. So I hope, just to make sure, do you see, yeah. Okay, good. So, okay, so when we say snarks have O of 1, which means constant verification time or proof size. What is meant is, what we mean is there's O, and here there's poly in security parameter O of 1. So that's really what we mean here, which means, you know, this equals, there's some poly in the security parameter, time. Now, what is the security parameter? It turns out that the security parameter must be at least logarithm of t. So what you really have here written is that it is also polynomial in the logarithm of the running time, which is exactly what we call scalable verification. Now, more to the point, you could also ask, why must it be, why must it be logarithmic in the, at least logarithmic in the proving time? So here's like sort of an argument. If lambda, the security parameter, is actually much less than the logarithm of the proving time, then what would happen is that the prover is assumed to have running time at least t. So the prover in time t can basically go over all possible proofs that would still take less than t time, because the amount of the information. Sorry, I meant to say if the length of the proof is less than log t, if the amount of information being sent is much less than log t, then prover can enumerate and find faulty proof of any statement. So yeah, this is why I think it's better to talk about. So even when you see in papers that snarks have O of 1 verification time or O of 1 proof size, usually it assumes that there's some group or some cryptographic structure underneath it, and then it talks about the number of objects in that world, but that world will always be of size that is at least t, so that representing an object there would be at least a log of t. And indeed, if you go to the snarks, let's say, that are used in Zcash, you'll notice that they are defined over curves and objects that have at least a size 2 to the 256 bits and even larger than that. So that's what the O of 1 means. Okay. Next question. Does redshift snarks from less polynomial commitment IOPs optimize the trade-offs between trust minimization and performance? So I would say that currently, optimizing anything, we're just too early in the game to say about anything that it is optimal. Redshift certainly is a good sort of sweet spot between different things. But for instance, I'll just give you one example. So Redshift which is, by the way, according to the definition, it is also a Stark. If you look at its proof size, as in other Starks, that proof size is considerably larger than other proof systems. Now, it's true that it has transparency. We'll get to that. And it is post-quantum secure. That's cool. But when I think of something optimal, I would like, and that thing, I don't know that it exists yet, right? But I would like something that has the shortest possible proof, you know, whatever, 100 bytes or less for 128-bit security, right? I would like it to have linear proving time. I would like it to have logarithmic verification time, and so on and so forth. I would like it to be transparent, post-quantum secure, so on and so forth. So right now, we just don't have anything that is optimal in all of the parameters that you have. But Redshift is certainly, you know, one very nice point that picks you know, optimizes certain things like other Starks, and, you know, pays in other domains. But yeah, so, and they're just, you know, maybe in 100 years, there'll be something that everyone will agree is optimal. We're just not there yet. Okay. Next question. Fractal is not a Stark. What's the property that disqualifies it? Okay, good. Very good question. So Fractal requires wait a second, you know, now I'm confusing myself. Just one second. Yeah, so let me just go back and share the screen. Okay, no, before I share the screen. Fractal, I'm starting to get confused with, like, now I'm working with 3 screens, right? There's the video where there's the crowdcast where the questions are, there's the whiteboard, and there's the Cambrian Explosion one. So the PowerPoint, so I'm just finding it hard to move. But you know what? Oh, I know what I can do. There's actually, in this one, what I did is I downloaded, oops, wait. Here, okay, good. I hope you see, so what I'm doing is I put the slides also inside the whiteboard, so I can do cool things like, you know, draw. Okay, so Fractal, which is right here, requires the basic system uses holography, which requires a setup that for the circuit it deals with is actually, the setup is not succinct. It is linear in the length of the circuit. Now, it's true that one of the applications that holography is used for in the Fractal paper is to sort of use it for recursively constructing an incrementally verifiable computation, or a proof carrying data system. And there, in certain settings, if you set it up correctly, you could also get a Stark out of it. But if you just use it with one invocation and use the very nice idea that is holography within Fractal, you actually require a setup phase that is transparent. So there's no trusted setup. There's no secrets going in, no toxic waste, but it is a setup phase that is linear, at least in the size of the computation. Great questions. Okay, next question. Ulysses Fractal as a snark. Does this in particular case mean that Fractal is not a Stark? Okay, I just answered that question, right? It's the same question. So Fractal, not in all settings, is a Stark. Again, if you just use it for one computation with the idea of holography, it would not be a Stark because its setup is transparent, but it's not scalable because someone on behalf of the verifier needs to run a computation that's more than logarithmic. Okay, but if you do it recursively, some of the applications there, yes, then it will be, but it's not unconditionally a Stark. Good. Okay, your Crypto 19 paper says MPC-based ZKP. Additionally, their communication complexity is non-scalable. It is square root T in the state of the art. Right. Nevertheless, for concrete circuits and amortized computation, verification time and communication complexity are extremely efficient. Could you please explain more which circuits Stark are better and which circuits MPC based are better? So that's a very good question, but I think that tailoring the very best setting of parameters or even the very best proof system for a given computation is something that is very much of an art and engineering, and involves many, many, many considerations. And I prefer, so I apologize to you. I don't want to answer this question in this talk, because it would just take us too much into the details. But square root n is in some settings very, very good, and it's certain, up to, it's a little bit like, you're doing fast multiplication. So when do you want to do multiplication? There are small integers where you just want to do it in the high school method. Above some level, you want to use the savings of Karatsuba, because the sort of high school method or the elementary school method is quadratic. And at some point, you want to do like Karatsuba, which gives you not quadratic, but like the time is like n to the 1.5 or so. For larger integer multiplication, you want to move to Tumkuk 3 or 4, and then as t goes to infinity, you want to use the FFT-based things. So to answer what is the exact setting in which you want to move from square root t to logarithmic or polylogarithmic in t, that's something that is too too detailed for me to try and answer now. Okay. But very good question. So I'm sorry I can't answer that. That would be a separate talk. Good. So let's continue. Okay, so now I'm going to stop sharing that screen and go back and share the other screen. Yeah, this is I think this requires almost the coordination skills of a of a pilot or something. Like a lot of multitasking. Good. So now, now I want to get to the sort of meat of the discussion, which is all of these proof systems and the many others that are out there currently, they share two common ancestors. All of them go through arithmetization, and all of them deal with the issue of low degreeness or low degree compliance. So that's from 30,000 feet above. And I want to explain a little bit what is arithmetization and what do we mean by low degreeness. And then we will see that the way you deal with low degreeness, the cryptographic assumptions you use to deal with it, and the arithmetization that you do, that's how sort of the world starts to break apart. So what is arithmetization? Arithmetization, it's, by the way, so those of you who have attended previous Stark at Home talks, basically, arithmetization is the starting point for everything that we did, right? And it is the process of reducing statements of computational integrity and problems of computational integrity to problems about local relations between a bunch of polynomials. And I'll just give an example. So for example, suppose you want to prove, the statement you want to make is that for a public 256-bit string Z that everyone sees, right? This is some hash. So Bob claims that he knows a pre-image of Z. So this is a very basic kind of computational statement, and indeed it's very combinatorial or computational in its phrasing. This is something that programmers deal with all the time. Now, before you arithmetize it, that's the claim that you have. I know Y such that if you apply SHA-2 to the input Y, you will get Z. Right? There's nothing that involves any algebra. The reduction now will produce a bunch of polynomials. In this case, maybe, this arithmetization that I'm imagining will produce two polynomials. One of them is called Q, and it has 4 variables, and the other one is R of X, a univariate polynomial, and also a degree bound. And what the reduction, the post-arithmetization claim will look something like this. I know 4 polynomials of degree D, let's call them A, B, C, and D, such that this weird red relation holds. Q, X, if you plug into the variable Y, the polynomial A of X, and if you plug into the variable T, the polynomial B, X plus 1, which is some weird twist on B. And if you plug into C, into the next variable, I got confused with all the variables. So you plug into Y, you plug A of X, into T, you plug B of x plus 1, you plug into C, you plug into T, into W, the last variable, sorry about that. You plug in C of 2 times x, it's supposed to equal D of x times R of x, right? And you claim that you know these 4 polynomials. So you started from a very computational statement, and now you're in this very algebraic statement. And then there are these magical theorems that turn out, like all the proof systems out there that are deployed have inside them some theorem that looks like this. And usually after you get the gist of it, these are actually easy to prove, or sorry, they're not easy to prove, but you get used to them. So you'll sort of notice them and identify them in all papers. They underlie them, you know, the snarks and the starks and the marlins and the fractals and the plonks and the slonks, they all have this thing. Right? There'll be some theorem lurking inside that says, well, you know, if A, B, C, and D are actually of degree D and they don't satisfy this relation, then it will be very easy to see that Bob is lying. And the other way around, if actually the statement is correct and the prover, you know, and Bob actually knows this Y, then it will be very efficient for him to produce those 4 polynomials. And then for any X that you check it on, you will see that things are good. So this is arithmetization, and it's very, very helpful in designing proof systems of computational integrity, both for scalability properties and for privacy properties. Okay, and indeed, if you assume this theorem, you can get a very scalable proof system, one that has a very efficient running time for the prover, and even an exponentially faster verification time for the verifier. You apply the reduction, so the only party that needs to do the reduction, well, I mean, you know, Alice, who's the verifier, needs to have somehow the polynomials Q and R. And then Bob needs to get the polynomials A, B, C, and D. All that Alice needs to do is sample a random X and ask Bob what is the value of A, B, C, and D on X. And then she sort of gets those values and plugs them into the statement. Actually, okay, she asks in the way we wrote it in this third cube down there, what she needs is she's going to ask, Bob, please tell me what is A of X. Tell me what is B of X plus 1. Tell me what is C at the point 2 times X. And tell me what is D at point X. And if you get all of those 4 values, then basically Alice can just basically check if this is correct or not. And everything works very well. So this is arithmetization. And now the main problem that we have now is that how do we enforce compliance with low degree? So that's the problem. We would like to have Bob commit to 4 polynomials, write them down somewhere, deposit them with some trusted notary. Each one of them is of degree D. And then we would like, after this has been done, we would like to sample a random X and then ask, what is the value of A, B, C, and D at those points? At the points that we care about. So A at X, B at X plus 1, C at 2 times X, and D at X. We would like someone to give us those answers, honestly. And that's the new computational integrity problem that we have. How do we force Bob to answer all of the queries according to some quadruple of pre-committed degree D polynomials? And I'll already tell you that if Bob will know where is the random query X going to fall, it would be extremely easy for Bob in all the proof systems that we're aware of to cheat and lie and basically prove anything that we want. So in all the proof systems we are aware of, you have this situation where you would like Bob to commit to 4 polynomials or 10 polynomials or 2 polynomials. You know, there are a lot of variations out there. And what kind of polynomials they are and over what finite field they are evaluated. But in all, you know, the common theme is that in all these systems, you want Bob to sort of mentally or cryptographically commit to these polynomials, then independently get the query and answer honestly according to the polynomials that are of degree D, where D is some specific parameter that you define. Okay? And so I'll soon go back and take some questions, but I just want to say that, so you might ask us, okay, so why isn't there just one proof system out there? Because they all do this thing. And the answer to that is that there are many, many different ways in order to enforce the low degreeness, in order to do the arithmetization, you know, how many polynomials you end up with, how do you encode them, what fields you're working over, and also, and probably most importantly, what are the cryptographic assumptions that you use in order to get the low degree enforcement? Because the sad reality is that we do not know how to enforce low degreeness without any cryptographic assumptions. We're just, you know, there's no way that we know how to do this. I mean, that's not entirely correct. For certain computations, you know, formally all computations in polynomial space, you can apply the very first kind of proof system that people thought about, which is called the framework of interactive proofs. So this is the framework from 1985. The original paper by Shafi Goldwasser, Silvio Micali, and Charlie Rakoff. That framework actually does not need any cryptographic assumptions, but it has a lot of problems. It's not as efficient with respect to, you know, general purpose computation. Getting zero knowledge there is a lot more tricky. The proving time doesn't scale as nicely. So all of the proof systems that you see deployed here will also need to revert somehow to cryptographic assumptions. So now I'm going to go back and ask some, you know, and take some questions. Okay. No low degreeness proof without crypto. Is it an observation or a theorem? Well, it's not a theorem, and I think it never, for it to be a theorem, you would have to, you know, in particular, you would have to prove things like P doesn't equal NP or something like that. Because if someone ever proves statements like P does not equal NP and goes much further than that, you could actually prove mathematically that certain constructions are, you know, you would get provable cryptography. For instance, you might, again, if someone proves P does not equal NP and things much stronger than that, you could also imagine that that person or someone else would prove that SHA-2 or some family of hash functions is actually a good collision-resistant hash family. And in that case, you will have provable, you know, theorem-based zero-knowledge proof systems, right? So it's only an observation. Good. Any other questions? Okay, cool. So let's go back and now start digging in and see how these different, you know, how do we parse this space? So I'm going to go backwards. I'm going to work. So we said there are three differentiating factors inside this universe of, or this Cambrian explosion, sort of like the different phyla and, you know, subfamilies of animals and creatures. We're going to think of it as whatever, paleontologists or geologists or something. We're going to look a little bit into this. And the cryptographic assumptions, there are 4 listed here. I should, let me just, I'm going now, once again, to move to this other screen because I want to get this thing straight. Just 1 second. Oops, sorry. So what I want to say is that there's actually one other family that I'm not, you know, that I haven't mentioned here. So let's just draw this sort of tree, and it may appear. And this is based on lattice-based. Sorry, actually the lattice-based maybe should lattices. And things like learning with errors and shortest vector problem and things coming from lattices. So the reason you don't see this, we don't see this as part of this whole world is that currently systems based on lattice assumptions are not yet ready for deployment. There's I think just one report on some initial from a team in Stanford that's trying to write a lattice-based system, or a system whose security is based, crypto assumption is based on lattices. So we'll put that on the side. It's not yet there, but maybe someday we'll have more of them. Okay, so let's go back to the screen. Okay, so we have here different assumptions. You have the collision-resistant hash, this biggest tree that has a lot of proof systems under it, and that's where the stuff that Starkware is interested in, and the stuff that at least I'm most passionate about lies there. You have stuff based on elliptic curve, discrete log problem, things like bulletproofs, and more recently Halo. You have things based on knowledge of exponent assumptions over bilinear groups, things in which the sort of the shielded transactions of Zcash relying on Groth 16 lie, and you have things based on groups of unknown order, which is some generalization of the hardness of assumption of RSA and things like that. Okay, and as you can see also, you can see the years, like collision-resistant hashes and their constructions go back to the 70s. Elliptic curve discrete log goes back to the 80s to aughts, depending on the exact variant of the security assumptions. Knowledge of exponent, again, there's like a 20-year span of the exact kind of assumption that folks are making. And groups of unknown order, again, they go back a while, but the variants that are needed for the recent proofs, such as supersonic, are more novel. Okay. Now, I also want to point out that this is a very inaccurate description, because you can take one idea and apply it in different settings. For instance, if you use this beautiful notion of holography and you instantiate it with a commitment scheme that is based on knowledge of exponents, you will get Marlin, and then it lies in one tree. But if you instantiate it with linear cryptography, you'll get something like fractal, which lies in a different tree. So you can take sub-techniques that are good in one area and apply them in some other area, and you'll get all kinds of improvements. So, if you take like the recent very nice lookup tables from the Plonk team from Aztec, and you move them to a system like in Halo or Zikabur or one of these others, you can of course use it there, and it could help. And or if you take the Fry protocol from Stark and you try to use it in some other setting, it could also be helpful there. So again, we're taking a very high level view at the sort of big family of proof systems out there. A big differentiating factor with respect to cryptography and post-quantum security is that the leftmost tree, which only requires collision-resistant hashes in order to be instantiated, and basically relies on symmetric cryptography. So we sometimes talk about the Stark version there as being a symmetric Stark, or meaning Stark based only, requiring only symmetric cryptography. That's post-quantum secure. Whereas all the stuff on the right requires all kinds of number theoretic assumptions that if you have a quantum computer, they would break. And so they're not post-quantum, or they're post-quantum susceptible. So that's one big differentiating factor that sort of emanates from the cryptographic assumptions out there. Okay. And what we'll do here is that, when you have, like, we'll give these tiny medals to different trees or subsystems there when they excel at one particular thing. So for post-quantum security, you give the medal to the, collision-resistant hash branch. And again, there's this also, someday we'll have efficient implemented lattice-based crypto systems, and they will also get this medal, okay? But they're not deployed yet. There are no... you can't really play with any proof systems based on them right now. At least I'm not aware of that. Okay. So the quantum secure medal goes to this little branch there. Now let's go. Okay, I'll stop here before we go to enforcing low degreenness, and I'll see if I just want to see if there are some questions. Good. Okay. Our lattice is not yet there because of theoretical issues with security efficiency issues, or just the novelty of the schemes. Well, I would answer, I think it's, Okay, it's not the security. Certainly, there's no issue with the security. Basically, the way systems work is you make a security assumption, and the security assumptions of lattices are, they're pretty well trusted. I mean, they go back a while. There's the Regev crypto system and Regev assumptions, and there's stuff going back to Dwork and Dwork. So I don't think it's the security of the assumptions. Definitely, efficiency is a problem. I think currently there are all the implementations or the works towards implementation are out there are in what is called the designated verifier model, which means that, if I want to verify a statement that you, Gua, are making, then I can generate some parameters and interact with you, and then I might get convinced. But if someone else wants to know that you convinced me, well, he's going to have to trust me or do the same process again. So that's a designated verifier. They also, I'm not aware of any suggested work, they're all theoretical, that is scalable, or even that has polylogarithmic verification. Some of them have short communication complexity, but I think that in most of them, the verifier running time has to be linear. Yeah, I think the verifier running time has to be linear. So they have an efficiency problem, and there's not a security problem, but in order to make the efficient, to go through to get something that is, for instance, scalable, even asymptotically and theoretically, you would need some theoretical breakthroughs and so on. Okay. Great question. Okay, next question. Recent breakthroughs in protocol design, such as recursive, wait, there was something voted up. Do you plan to write a survey of ZKP, or could you please recommend some academic survey papers covering the Cambrian explosion of crypto proofs? Yeah, someday I want to write a survey. Maybe when I retire. Okay, I mean, no, seriously, someone should write a survey. I would love to write a survey, at least on the symmetric stuff that I'm most passionate about. Yeah, I mean, there's a paper from 2015 about delegation of computation, which is slightly related, but it's pretty outdated by now. So most of the systems appearing here are not covered by that. So, yeah. I mean, I wrote a blog post that I shared, and I'll maybe, I'm guessing someone will share the link there, but yeah, someone should do it. And okay, I see Amir is saying here there's another survey. I've not read it, so oh, now I remember. I think that I sent the link to Amir and I said I have not read it, but please recommend if it's so there is a survey. Good. Okay. Next question. Recent breakthroughs in protocol design, such as recursive proof composition described in Halo, have undoubtedly increased protocol complexity. Given what is at stake, no pun intended, in crypto networks, is there a concern that the added complexity might introduce risks and thereby decrease the use of snarks in favor of better understood snarks? At this fast pace of development, when you consider something safe? So, wait a second. First of all, Halo is not a Stark. Okay, so I agree that Halo has added complexity, and any new proof system that comes out there has its complexity, and it should, be scrutinized and peer-reviewed and so on. And to answer the question about when, when can we consider something safe? It's really a matter of, I don't know. I mean, some people would say that public key cryptography based on number theoretic assumptions is not safe. Not just because quantum computers are around the corner or something. I don't know, till we have proofs, we don't really, I mean proofs of cryptography. So I think in cryptography, first of all, on the theoretical level, as time goes by and more tires are kicked and more people use it, it's probably safer. And we'll get to this sort of Lindy effect in soon. That's one thing. And yeah, there's also the whole, are there bugs in the code kind of question. And yeah, I don't have anything smart to say about this. Definitely, as new protocols come in, they add complexity. I just want to say that I think the complexity in Halo is not the complexity in Stark. It's I think it's a greater level of complexity, and not everything is fleshed out there yet from a sort of formal security point of view. But the statement that any new protocol should be scrutinized, peer-reviewed, examined, and then its implementation parameters should be examined again, that's a truism. Okay. Next question. Could you tell us an author or reference for the work on lattice-based systems? So I think someone already answered. There's the closest thing to implementation is a report from Stanford. I'm hoping someone will add it in the comments. So I don't know if it's it's a single authored paper from Stanford saying we implemented some of the systems from Bonnet et al. And it's a very preliminary implementation. I'll let someone, I'm sure someone can look it up. It's something very recent, and that's the latest I'm aware of. Okay. So let me go. Oh, I forgot to say start answering, done answering. Sorry. Start answering and done answering. Good. So let's go back and continue. So the next aspect I'd like to discuss is enforcing, how do you enforce low degreenness? And here again, there's a lot of, again, this is a very, very high level view. And even this distinction does a lot of, a disservice to all the nuances of different ways that you enforce low degreenness. But at a very, very high level, 3 of the trees use various kinds of commitment schemes. So some of them are linear commitments, like bulletproofs and Halo. Some of them are not even linear commitments, all the ones on the leftmost side. There's no sort of additive homomorphic structure that one can use. And some of them are polynomial commitment schemes, which are a different creature, and they appear in the sort of in this red tree. And under the and even there's some this slide is not updated. So the red tree should not be all red. So inside the systems that are based on knowledge of exponent, some of them work not just by offering a commitment scheme, but by, remember that we talked that in arithmetization, there's this query X that is going to be sent after you commit. So actually the trusted setup in the Pinocchio and the Groth 16 system, what they do is the trusted setup hides the query to the polynomials in the trusted setup phase. So, but the other systems like Sonic, Plonk, Slonk, and Marlin are actually commitment schemes. So most of the systems out there, they use some form or another of a commitment scheme, which basically, in a somewhat straightforward way, says, let us have the prover commit to the polynomial, then let us have the prover evaluate the commitment on some random X, roughly speaking. There is a very important sub-branch that has extremely efficient proofs, the Pinocchio and the Groth 16 branch. It's inside the knowledge of exponent one, that does something that is more powerful in terms of assumption, and it hides the query to the polynomials. And because of that, it also gets much shorter proofs. So in general, if you go to number theoretic constructions, you are definitely shrinking the proof size. And the shortest of the proofs, the medal for being the shortest proofs available goes to the sort of Pinocchio and even more so to the Groth 16 construction within the knowledge of exponents. So this branch gets that medal. Famously, Groth 16, which is currently used in Zcash and other places, a single transaction, its proof is less than 200 bytes, right? And all these other systems have much larger. And if you go to the left, you get really, really long proofs in the dozens of kilobytes, because they contain a lot of sort of Merkle tree paths, and basically on the right-hand side, there's all this homomorphic additive structure that comes from number theoretic constructions that allows you to compress things a little bit more. And on the left, there's really no structure, which is why they are more quantum resistant and leaner cryptography. But because of that, things have to be more verbose and that's another sort of trade-off. So there was a question previously about redshift. Is it the optimal, this or that? So according to the length of proofs, it is not there. So it goes on the left with a bunch of the other proofs, and then it doesn't get the shortest, that method it does not get. Okay, so let me go back before we deal with arithmetization and see if there are more questions. Good. So Guha is asking, if one is willing to sacrifice quantum resistance, can one shrink snarks by using, e.g., class group-based vector commitments instead of Merkle trees? So the answer to that is, not only is this possible, but this actually has been done. So we'll get to transparency in a minute. So, okay, so yes, the answer is yes. Not only is it possible, but there are a bunch of works that have done that already, and probably we'll see more and more of them coming. And yes, and indeed what you get is you sacrifice the quantum resistance, you sacrifice a few more things like the efficiency goes down a little bit in terms of proving time, but you definitely also can shrink the argument length. Yeah, so it's a great question. Okay. Okay, good. So we handed out 2 medals right now. Let's see what else, what else we have. So now let's talk about arithmetization, which is what is the algebraic world into which you're reducing your statements in order for them to be proved. And here again, so the kind of cryptography that you're going to use for enforcing low degreeness is going to a large extent to dictate the kind of field you're going to embed your computational statements in. And the systems on the right that are number theoretic in their nature require large domains, because that's what in order for them to be safe, you need that size of moduli or integers to operate there. So as you go to the right, if you start with the elliptic curve DLPs, you need 256-bit primes or larger, and then it goes slightly larger for different variants of the knowledge of exponent assumptions. And if you go to the systems with groups of unknown order, that some of them can actually be also transparent, you end up with moduli that could be in thousands of bits if you're looking at RSA integers. Whereas at the left, so the lean cryptography, the way these systems work is that you need the cryptography only for a commitment to, basically only for some Merkle commitment. And because of that, like everything else is proved in an information theoretic way. And basically you can work with any kind of arithmetization that you want. You can work over binary fields, over fields of characteristic 3. You could use fields that are as small as 16 bits or 32 bits, depending on the size of the computation, but the cryptography would still work and the systems would still have some safety to them. There are all kinds of issues when you work with small fields, especially when you try to make them non-interactive, but at least there is a way to get it done in this world. So when it goes to speed and like fast arithmetic, you give this medal sort of to the leftmost branch. Now let's talk a little bit about scalability and transparency. So we're handing out a whole bunch of medals for transparency and scalability. So remember there was this question, I think Guha asked it if I'm not mistaken, can you sacrifice post-quantum security and still have transparency? So if you remember, there was this line here between, so the post-quantum secure stuff is the tree on the left and everything on the right is not post-quantum secure. And you can see that some things there are transparent. So bulletproofs and Halo and supersonic they are transparent. Of these 3, the only one that is scalable there is supersonic, bulletproofs and well, okay, Halo, it's depending on the details that will come out. So I haven't seen enough to be sure that again, as t goes to infinity, actually the proof size scales as polylogarithm of t. But so the jury is out there. It might be scalable. I don't know. I'm just the papers I've seen have not made that claim, but maybe it will end up that way. Bulletproofs is certainly not scalable. It is transparent. Supersonic is both scalable and transparent. And Marlin is transparent. Sorry, scalable. Okay, so you see there's a whole bunch of things that are scalable and transparent, but I want to say that the whole tree on the left, you'll notice that all of it is transparent, right? There's no trusted setup there because of the kind of cryptographic assumptions used there. And many of the systems are also scalable, but not all of them. And you'll see here, there was a question about fractal. Why isn't it a Stark? So as you can see here, if you use holography, which is the main component there, then after a linear preprocessing phase, it does become scalable, which is what we call semi-scalable. But it's not purely scalable like what we demand from Stark. So we give the sort of transparency prize to a bunch of, right, there are several systems out there that share the transparency prize. And then scalability, it's more nuanced, right? Some of, look back here, some of the systems are, some are not, some are semi-scalable. So now I want to go back and basically answer more questions. Okay, are there any questions? Okay, so I'll go back. Just remember, any question that you have, just pop it up there. I go back from time to time and check to see if there are any questions. Okay, good. Kial, what are the most promising research areas you think everyone interested should keep track of? Oh boy. I can tell you what my favorite question is. I just love soundness analysis of low degree testing in the transparent world. That's my favorite, but I'm sure that's my own skewed, biased view. It's not okay. When I get to write that survey on there should be a section that says here are the most promising research directions, but I'm not qualified to answer off the top of my head right now on where the most promising. And you know what? If I had to answer, I would say the most promising, or if we look back 10 years from today and ask ourselves what were the most amazing things. So I'm pretty sure that it will be the things that no one expected or anticipated. So I think looking back 10 years, I think one of the most amazing results in this area of sort of the larger area of computational complexity that spawned all of these proof systems is actually this completely amazing result that MIP star equals recursively enumerable computation, which is completely mind-blowing. So sort of the quantum version of interactive proofs, of multi-prover interactive proofs, that is equivalent to sort of the IOP model in which many Starks and other systems are built, which is equivalent to the PCP model. So that model is called the MIP model. And if you allow the provers there to have quantum entanglement, then the class of computations that can be succinctly verified goes up to be basically anything that can be computed at all with no bounds on running time, which is absolutely mind-blowing. Now, if you asked anyone 10 years ago what would be the most spectacular or most interesting research direction, I don't think anyone would have said, oh, looking at the quantum analogs of proof systems. It wouldn't have been my bet. And I was doing research on proof systems 10 years ago. So it came completely from left field. And so that would be my prediction. The most amazing stuff would be stuff that we can't even raise a question right now. Okay, I have a question for the ARC in Stark. Why is an ordinary signature not an argument of knowledge? I do proof knowledge of a private key by signing a challenge. So it should actually be something like a knowledge argument. So for a system to be an argument of knowledge, one has to define a knowledge extractor, which means there should formally be an efficient machine that interacts with the the party giving the proof, and extracting from it a witness. I think that some signature schemes would be, signatures of knowledge and arguments of knowledge, but not necessarily all of them. So yeah, that would be my short answer to that. Next question. What do you think about dark systems? These are in the last tree, but have a general construction to provide efficient, transparent setups. So dark and supersonic, right? You're right in the left tree. So first of all, I think they're great. I think if I haven't said this, I think all of these systems are great, and I think the fact that we're seeing tons of research on all of them is amazing and spectacular and really, really great, and it's advancing knowledge and the state of the art and everything. Okay, now it's true that I am biased towards a very particular branch, which is the one that I'm researching, but that's the way of the world, and others, the people behind dark should be extremely proud, and rightly so, of their system, and has a lot of good advantages and so on and so forth. So what I would say about dark is that yes, it is a general construction. It does have an efficient, transparent setup. Yes, so it's definitely good. I think ours are more efficient and better. They're also not post-quantum susceptible. I think they should have faster provers because of the leaner cryptographic assumptions. But I have nothing bad to say about any one of these proof systems. They're all great, and we'll see more and more of them, and that's terrific. Okay, so let's go on. Now I want to talk about the sort of future proofing of the financial highway, and let's look at it through the lens of the Lindy effect, which says that the future life expectancy of some non-perishable thing, like a technology or an idea, is proportional to the current age. And according to that, so this goes back to the question of when can we trust systems? So my biased answer would be that if the construction is peer reviewed and it seems that the math is working and so on, I would still want my systems, if I'm putting a lot of value on them, I would prefer them to reside on stuff that has been out there for a long time and has been used by a lot of infrastructure out there. So if you go, so the stuff like the groups of unknown order, currently they're not supporting yet anything. I mean, the Chia VDF is riding on class groups, which are some form of group of unknown order, but so there's some value in real world things starting to sit on the rightmost thing. On the knowledge of exponent and the forms used by snarks, one would say that Zcash and the many other systems that are like it and use the Gross 16 snarks, they sort of they're out there for like almost 4 years if you're looking at Zcash. And there's, depending on the daily value, there's roughly $500 million of market cap there. So that's something. Elliptic curve DLP is already in the billions of dollars. A lot of SSL key exchange and identity-based crypto. It's been there out there longer. And again, I'm biased, but it is the truth that things relying on SHA-2 or SHA-3 and hashes, basically all of the infrastructure of the internet with its trillions of dollars requires these as assumptions. So I would say that according to proof readiness as a technology, the prize should go again to the leftmost tree. And now I want to summarize and then I want to answer questions. So all of your questions, this is the time because we're near the end. So there's this Cambrian explosion that's ongoing. I apologize to all the systems that I didn't include here because I based it on slides that are already a few months old. The ZKP members, and again, I'm doing huge disservice to sort of taking all of this brilliant work of so many brilliant people and sort of mushing it up into a few simple statements. I apologize for that. But at a very high level, the ZKP members differ by their arithmetization means, by how they enforce low degreeness and what cryptographic assumptions they use to underpin that low degree compliance. There are various prizes. I'm sure there are others and more, but these are the ones we discussed or I chose to discuss today. It's a very, again, biased choice. I would say that for short proofs, if you want your proof length to be very small, you want to use the Groth 16 snarks, or in general things coming from the hiding query sub-branch of the knowledge of exponent tree, which is the second to the left. And I think that for everything else, there's starts. But again, I'm of course, it's not a secret that I'm affiliated with Starkware, and we're behind Stark. So you take that with a grain of salt. Yeah. So now I'm going to answer questions, and we'll wrap it up. Okay. Aside from blockchains, or as primitives to enforce honest behavior in other protocols like MPC, do you know or envision uses of general relation ZKP in other areas? Great question. So yes, I believe that so proof systems, and it's not, MPCs offer even more, because proof systems are like the simple version of secure multi-party computation. Basically an asymmetric setting in which only one party has a secret, or one party is doing all of the computation, just proving integrity to everyone else. So, but even ZKPs, I think, will be at t equals infinity. So they will go out of blockchains into use by society, because society will expect and demand even the largest and the strongest of the institutions to operate with computational integrity, and to sort of be able to monitor the computational integrity of those huge parties. And the way this will be done is that the huge parties, the governments, the monopolies, the financial institutions of the world, they will prove the integrity of their computation. And in some cases, they will also do it using privacy, because privacy will be needed. Maybe there's some medical data and so on and so forth. So I think that's going to be, it's going to start with blockchains, but it's going to merge to all of society. And then secure MPC, which is, one level above zero knowledge in terms of the complexity of the interaction between parties. Again, it will also apply to all of society. So I think that at some point, everyone, when we're running auctions, or when the government is running auctions, or when exchanges are operating, it will be using secure multi-party computation to ensure fairness and things like that. And that's not the end of what cryptography has to offer to the world. There are other areas in which I'm not an expert. I only know the terms. There are things like differential privacy that sort of protect the privacy of our data as it's being computed on and aggregated. There are things like homomorphic encryption that will allow us to store our encrypted data on the cloud and then have computation applied to it. There are things that are now being actively discussed in academia. How do you use cryptography to enforce sort of social fairness when all of these algorithms are doing machine learning and so on. These are areas I know of. I'm not an expert on, but I'm just mentioning them. You should read about them. Fairness and differential privacy and other things. Okay, do you think arithmetization and low degreenness are standard? Does it exist? Do there exist other ways to convert circuit for ZKP? So yes, there are other ways to convert circuits for ZKPs, a whole bunch of other ways. If you go to the original work, protocols on zero knowledge proofs, they did not use arithmetization at all. They used sort of commit reveal schemes, all kinds of variants of the where's Waldo kind of thing, where you basically hide something and you open it up from different ways. So definitely they're not the only way. They are extremely efficient and sort of malleable in a good way. There's a lot you can do with them. With polynomials, I want to say that in many respects, they're not even the end of the technology. There are things that in certain aspects are even better. Things like algebraic geometry codes, which are sort of one level. But I mean, polynomials and then standard arithmetization using polynomials is basically a special case, a genus zero kind case of algebraic geometry codes. So they're even higher algebraic objects out there, and yeah, it's certainly not the end of our understanding. And then we mentioned there's lattice-based constructions that may come to play. Okay. Next question. Amir, what is the crossover for verifier time with cross 16 and Starks? Is the verifier time just proportional to the number of gates in the circuit? So cross 16, I don't know what the latest numbers. They're in the very few milliseconds for a small fixed circuit like Zcash. I remember under 10 milliseconds, maybe it's 5 or so. The Ethereum Foundation ETH Stark code that we'll be releasing in roughly a month or so will also have its verifier in the 5 millisecond range. So I would say that for similar kinds of computation, roughly the verifying time of Starks and Groth 16 snarks would be similar. I think one area where Starks behave better is that if you have many inputs and you need to feed them, many public inputs, and you need to feed them into the verification process, because with Starks you have linear cryptography, then it scales practically wise. I mean, asymptotically they sort of look very similar because you need to process something with each one of the inputs, but practically speaking, because of the linear cryptography, I think Stark verifiers are going to be more efficient when you have very large public inputs to them. But I would say that verification time, I mean, there's something interesting here. So a snark verifier in terms of size is much smaller. Sorry, a snark proof is much smaller. It's 200 bytes or so, a Groth 16. But verifying it is pretty much the same number of milliseconds currently as the much longer Stark proof, because in the Stark proof, what you're verifying is a whole bunch of hashes, and those are extremely fast. Whereas in the Snark, you have group operations over an elliptic curve group, and that's more. Other than efforts like Zero Knowledge VM, are there other efforts to open up access to ZKP libraries for developers at large? Yes, there are a ton of them. I'll mention a few that I am aware of. So I mentioned Starkware in about 2 months. I mean, or 3 months or so, we have committed to release a very efficient prover and verifier. And I hope that not the next Stark at Home, but maybe one after that will be dedicated to going over the open source code for this thing. And we already tweeted that we will have provers that are 20 times faster than the very fastest other prover out there. So that's one open source thing. I saw that the Aztec team has announced actually a collaborating effort. I think I saw it yesterday for collaborating on plonks and things like that. I think the ZK Sync project from the Matter intends to have its stuff open source. Everything that Zcash does with its Groth 16 snarks and then soon with Halo is, so whatever is already in use is open sourced, and more stuff will be open sourced. You have Socrates and a whole bunch of other things. I'm probably missing out a whole bunch of them. Yeah, but there's a lot, and there will be a lot more. There's the Zexe, there's libiop, there's libstark that when I was in the academic world we released, and the list goes on and on. I think there's a reference, like if you go to ZK Science or zkpscience.org, maybe that's the website, you'll see like this huge list of everything that's out there. From your perspective, what has been the most surprising insight from complexity theory, let's say since IP equals P space? Oh, I mean, so much has transpired. Quasi-linear PCPs, and even MIP equals next is just completely mind-blowing. I just mentioned this amazing result, MIP star equals RE. I mean, man, that's like, unimaginable, because RE, like recursively enumerable, is stuff that, it's the halting problem, right? And then the fact that you can verify it in something that maybe physically is realizable, right? If quantum mechanics hold to large things, it's just unbelievable. Yeah, there's a bunch of other things, of course. I mean, there's so many important results, graph isomorphism being in quasi-logarithmic time, Scholl's algorithm. Yeah. Okay. Practical questions. Are R1CS, as in Groth 16, and AIR in the case of Stark, standard in terms of representations for arithmetization, or are there other representations being used? Which would you consider as easier representation to construct a compiler from a somewhat high-level language? Okay, so the answer is that at the current nascent state of the space, sadly, nothing is standard, and no one of them is exactly, in one sense, they're all easy, but you want something that is easy and efficient. What do I mean? So you can take any computation and sort of break it out into a Boolean circuit, and then each one of these gates in the Boolean circuit you could easily represent as an R1CS or under the AIR system and so on. The only problem would be, so it would be very easy, but it would be just horrendously inefficient. We don't yet, I mean, again, this is progressing towards that point. We don't yet have a good, simple tool chain where if you're a developer and you want something standard that you can just work with, it's not there yet. There are initial attempts to go in that direction. So for instance, Bobbin is working on things like AIR assembly and AIR script and the sort of virtual machine that is keeps on getting improved, that goes down the AIR kind of route. There are things based on R1CS, like I believe Socrates and a few others, but we're still early in the game. You know, it will take a little bit more time for it to become more usable, but it could be usable in the R1CS world. It could be usable in the AIR world. And both of them are needed and important. Okay, so I just want to wrap up and go back to the talk, and basically, I think just want to say that we summarized. I really enjoyed this one. I think that there were a lot of very good questions. Again, I apologize for taking hundreds of papers of really deep math and many months or years of brilliant mathematicians and cryptographers, and sort of saying, oh, they're like whatever, 2 or 3, here are like 4 awards, and it's of course much more complicated than that. But I hope that at least those from outside the field, this gave some sort of a feeling for, or a high level view of what's going on. So in 2 weeks, we'll meet again. I mean, if you'll show up, we'll definitely want to do something more. I need to think a little bit more on what would be a good next topic. I hope that the topic after that will be, and then I'll actually invite someone else to lead it, will be to talk about the code for eStark. And again, this will be open source code, very efficient prover and verifier. So we really hope that folks will use it. So if you have suggestions for stuff that you want to talk about or hear about, things like maybe a survey of different kinds of interactive proofs and the various acronyms there, ZK and IP and MIP, PCP, how they differ, what they brought to the world. That's one option, explaining what zero knowledge is and what do we mean by arguments of knowledge and knowledge extraction and that thing. Those are other options. Yeah, thank you very much, and I hope to see you again. We did fry, but what about deep fry? Yeah, that could be another. Yeah, that could be another thing. Yeah, I think deep fry and the deep aspect. Yeah, that's another option. Thanks for the suggestion, Adrian. Okay, thank you for all the compliments and the thanks. I just want to say that I'm enjoying it tremendously, and I really like this. As a scientist and researcher, being able to share knowledge and talk is really fulfilling and gratifying. Thanks so much. Okay, so I will now stop the broadcast. Till next time, stay safe and healthy.